Hello, everyone. Thanks for being here for my presentation. Today, I would like to introduce our work, BurstZ, a bandwidth-efficient scientific computing accelerator platform for logistical data. This work is done by Gongjin Sun, Zhengyan Kang, and Sanwoo Jiang. Gongjin Sun and Sanwoo Jiang are from University of California, Irvine, and Zhengyan Kang is from Kunming University, Korea. I will first introduce the bandwidth bottleneck of large-scale scientific computing acceleration. Then we will propose the hardware optimize the floating point compression as a solution to address this bottleneck. Finally, we will use a typical application, sensor computation, to evaluate our work efficiency. As we know, a lot of high-performance computing applications have to deal with extreme amounts of scientific data, such as climate simulation, cosmology particle simulation, molecular dynamics, and combustion simulation. Actually, many of them are floating point intensive. This large scientific data propose challenges to existing accelerators. If the working set can fit into onboard memory, the accelerators can work in extremely high performance. But if not, the performance will be bound by data movement across PCIe. Here we show a typical bandwidth comparison between PCIe and GPU. A PCIe Gen 3 by 8 can provide almost 8 gigabytes per second bandwidth. By contrast, an NVIDIA RTX 28 Ti GDDR6 can provide more than 600 gigabytes per second. You can see there is a huge gap between them. So instead of the accelerator's computing capacity or memory bandwidth, it's the PCIe that becomes the performance bottleneck. As a further illustration here, on the host side, we have various fast storage on memory. We also have various accelerators, including GPU, FPGA, and other types. These accelerators are usually working very, very fast. However, the PCIe link, which bridges these two paths, is usually slow. As a result, the data movement overhead in the PCIe becomes the primary bottleneck. One potential solution is data compression. The data compression has been widely used in various areas, and it can effectively reduce data store requirements and the data movement amount. But the high throughput of the data compression is the key point, because it must provide a high throughput to accelerators. Typically, compression algorithms can be categorized into two classes, non-floating point ones and floating point ones. They usually target different data formats. One factor is existing non-floating point compression schemes, such as RZ77, 78, gzip, RZ4, and so on, do not work well with floating point data. One test we made in real scientific data sets show ZFP, which are typical non-floating point, which are typical floating point compression, can achieve 7 times the high compression ratio than gzip, which is a non-floating point compression. Actually, gzip has almost no compression. There are a lot of existing floating point compression schemes, including ZFP, SZ, FPZip, and so on. Among them, only ZFP and SZ are error-controlled, which is a big advantage over other schemes. ZFP is based on block transformation, but SZ is based on value prediction. In this work, we target ZFP for optimization because it's easier for ZFP to be hardware optimized than SZ. Actually, the vanilla ZFP algorithms has low throughput both in software and FPGA, and it's too slow to support the accelerator. We identified the bottleneck of ZFP as the bit encoding stage, which uses what's called group testing. A group testing can sometimes emit only 1 bit at a time, severely limiting the performance. So we propose SZFP, a highly hardware optimized ZFP. It's a variant of one-dimension ZFP that processes the one-dimension blocks. SZFP has two optimizations. The first one is use an efficient header-based encoding. Here is a data layout of a one-dimension block. SZFP split this block into 3 different regions and processes them differently. So SZFP can process more bits per cycle than the original bitwise encoding. The second optimization SZFP uses is it splits the compressed data into multiple aligned chunks. Each chunk has 60 kilobytes with a little padding bits. Each chunk can be decompressed independently from each other. So we can feed multiple chunks into multiple encoder or decoders simultaneously and highly parallelize the encoding or decoding process. SZFP not only has features of the original ZFP, but also has some of its own unique features. It has a much higher decompression compression speed, a smaller chip resource utilization because it uses a simpler algorithm, but it has a slightly lower compression ratio than the original ZFP. It should be noted that the main purpose of our SZFP is to reduce data movement instead of pursuing beating the original ZFP. We use a typical application in this work, stencil computation. The stencil computation has been used in many important scientific applications, including scientific simulation, earthquake or weather prediction, and so on. Here is a 2-dimension 5-point stencil. Each point in the grid has to be updated by all its neighbors' values. Now here is a 3D stencil computations, 7-point, 19-point, and 27-point stencil. We used a simple 3D 7-point stencil for general demonstrating BurstZ in this work because our focus is not our fastest stencil code, but the whole system. I will briefly introduce the basic principle of our 3D stencil computation. First, this 3D grid represents the whole data sets, which resides the external large volume data storage. And then, to begin the calculation, we first split the whole data set along the vertical direction into a series of XY planes. To calculate the one XY plane, we have to load 3 consecutive planes. Since our onboard memory is limited, we only keep 3 plane buffers on the onboard memory. Also, since accessing onboard memory has a relatively long latency, we also keep 3 row buffers on the on-chip memory, which corresponds to the 3 planes on the onboard memory. Each time, we load 3 rows from the onboard memory into on-chip memory. Once we finish the calculation of one row, we keep loading next rows until we finish the calculation of our whole XY plane. Combining the mentioned SZFP and stencil computation, we propose BurstZ, a compression-based accelerator platform. Here is the overall architecture of BurstZ. On the left side is the host, which includes the memory or storage. On the right side is the accelerator, which includes the onboard memory and a computation engine. As we discussed before, the PCIe is the bottleneck. So we can first compress the input data and store them into the host side. Then we can transfer the compressed data over PCIe into the memory, the onboard memory of the accelerator. But the computation engine still needs the uncompressed data. so we can deploy the multiple decompressors between them. These decompressors are responsible for decompressing the compressed data on the fly and feed them into the computation engine. Once the results of the computation engine are floating out, they will first into multiple compressors. The compressors are responsible for compressing them and then send them back to the memory, onboard memory again. Since our compressor and decompressor can work in a very high speed, there will be no bottleneck here. Actually, there are lots of interesting design issues here. Please see the paper for more details. For evaluation, we are using real-world datasets which are from scientific data reduction benchmark. We use the Xilinx VC707 as our prototype platform. VC707 is an old chip which has a PCIe Gen 2x8, which can provide 4 gigabytes per second bandwidth. It also has a 1 gigabyte onboard memory, which can provide more than 10 gigabytes per second bandwidth. Here we show the BurstZ's resource utilization on chip. One combination is platform plus 3 decompressors and 1 compressor. With VC707, the resource utilization of our BurstZ is less than 50%. So the majority of the chip is left for the accelerators to use. With a more modern chip, VCU118, the total resource utilization is even less than 5%. So we accept the higher performance with this modern chip because we can place more compressors or decompressors there. This figure shows the compression ratios of SZFP across 4 benchmarks. We also show the compression ratio of GZIP for comparison. Our SZFP shows 4 different configurations with different error bounds. These realistic error bound numbers are taken from existing research. We can see our SZFP can provide 5 times up to 5 times high compression ratio than the GZIP. Also, as the error bounds increase, the compression ratios of SZFP decreases. We saw that ZFP has much better compression with lax error bounds, such as with 0.001, but SZFP did similar against the ZFP with stringent bounds. In any case, we show that typically the compression ratio is consistently good enough to remove the PCIe bottleneck. This figure shows the compression throughput of SZFP across 4 benchmarks. You can see for the first 2 error bounds, our SZFP can achieve very high throughput, which are close to the wear speed, which is 8 gigabytes per second. We also implement a FPGA version of the vanilla ZFP without any modification. We can see just simply transplanting a software algorithm into a FPGA without any modification may not be able to improve the performance significantly. We also show the throughputs of the software ZFP. So we can see our SZFP can provide up to 7 times high throughput than a vanilla FPGA. This figure shows the decompression throughput of our SZFP. Similarly, our SZFP can provide up to 4 times high throughput than vanilla FPGA. Finally, I will show the BurstZ overall application evaluation. In this evaluation, we use 8 configurations. The large map is used as a baseline. which represents BurstZ stencil code with enough memory to hold the dataset. As a result, the PCIe bottleneck is removed. All other configurations performance have been normalized to this configuration, large man. The first 4 bars represents BurstZ with compression, different error bounds. The smaller error bounds are the higher performance the BurstZ has. We can see our BurstZ with compression is faster than large man, because the accelerator can even remove the DRAM performance bottleneck. The red 4 bars represents the configuration without any compression. Here is the no comp, which represents BurstZ stencil without any compression. We can see the PCIe bottleneck plays a big role in slowing down the performance. Here is the faster map, which represents BurstZ stencil with unlimited DRAM bandwidth, but the PCIe band still exists. As we discussed in the beginning of the presentation, even the accelerators can have a very high DRAM bandwidth. It's still bottlenecked by the PCIe. So we can see it's worse than all of our BurstZ version configuration with compression. We also provide 2 ideal cases, 2 ideal configurations. One is ideal, which represents BurstZ with unrealistically large on-chip memory. So we can place all 3 pins into on-chip memory. But since the whole dataset still resides into the external storage, the PCIe bound still exists. The last one is ideal large, which means ideal with enough memory to hold the whole dataset. As a result, the PCIe bottleneck is removed. Among these 4 configurations, the ideal large gives us the highest performance, but it's still not better than our BurstZ with compression. Take the brown benchmark for example. Our BurstZ with compression can provide up to 4 times speed up than the no comp configuration. It also provides more than 2.5 times speed up than the ideal configuration. Even compared to the ideal large, our BurstZ with compression still can give us more than 40% performance improvement. By conclusion, we present BurstZ, a bandwidth-efficient scientific computing accelerator platform for large data. BurstZ uses hardware-optimized floating-point compression and removes the PCIe bottleneck of the accelerators. And BurstZ actually is a general platform. We will use it in many more applications. Thank you.